So I'm creating a short video about the derivation of the relationship between the period and length for the simple pendulum. Remember that the simple pendulum is a way of representing simple harmonic motion. And there is nice information in the simple pendulum that allows us to do a lot of things. One is we can determine the acceleration due to gravity by using the simple pendulum and looking at its period and its frequency. We can also learn about some of how we work with approximations and where do those approximations come in, and why it is important to understand how we use those approximations and how it impacts what we see and how we can use it. So let's look at our simple harmonic motion and let's look at the pendulum. So we've got a pendulum here. And in this pendulum, we're writing down the various forces. And remember, forces are directional. So if I've got a length of string here and the mass at the end of my pendulum, and that's a critical item for a simple pendulum, is that you have a mass or a bob that significantly has more mass than that of the string or the wire that's working with it. If I had a rod here, that would be a physical pendulum, and I'd have to include moment of inertia. But here I don't do that because the mass that's going to be controlling the action and the forces that are controlling the action are going to be represented by that center of mass point in the mass of my bob. So let's look at our forces. So we've got tension in the string, and then we have the force due to gravity that's directly in line with that tension, and that's going to be the mass times the gravity times the cosine of this angle. So it's going to be like working with an inclined plane, but we're going to be looking at that. Now my tangential force, or the restoring force that's going to be wanting to guide my pendulum back towards the center, or the equilibrium point where it's going to be here at the bottom of the swing, that's going to be my tangential force, which is going to be related to the acceleration due to gravity and the sine of the angle. Now, we're going to go back and compare this with Hooke's law, because when we derive simple harmonic motion, we're using that spring on a mass bobbing up and down to really give us that understanding of that restoring force. So we can do that. So I've got Hooke's law here, but if I'm traveling in an arc, we use that S to represent the arc length. And that S is going to be related back to the length of my pendulum and my angle. So we can refer to the angle as S divided by L, or we can look at S as being L times the angle, and we can actually look at that. So basically, we want to make sure that we're dealing with that. Now for the small angles, less than 20 degrees, the sine of the angle, if I actually calculate it out, is going to look an awful lot like the angle, particularly when I'm in radians. So when I'm in radians, that sine of the angle is approximately equal to the angle itself. And so as long as I'm staying in a 20-degree range, I can actually use the angle instead of doing the sine of the angle. So we can make that substitution. So that's what I've done here. We've done our K. Now remember, K is the spring constant, and that spring constant is a physical definition of my spring. How compact, what kind of restoring force is in my spring. So I've got that, and we're going to use X. That S is the distance traveled. So there it is. I've got the negative here. I've got the negative here. The negatives are going to cancel each other out. And I can substitute S divided by L for the sine of the angle. And I can rearrange this to get K over M is equal to gravity over the length. Now, why would I do that? Why would I do that? Well, I would do that because when we derived and looked at those equations of motion with that spring problem, I'm able to relate back to my angular velocity, which is 2 pi times the frequency, is equal to the square root of K divided by M. which now means I can relate frequency and period to that physical construct of my pendulum. So now if I rearrange everything, I get the square root of k over m is going to equal the square root of g over l. And I can rearrange to solve for my equation here to look at the period, or that time that it takes to swing a complete cycle, start through the equilibrium to the other side and back again. That's the period of one complete cycle. I can rearrange it and work with that. And then we can look at how the length and the period squared are related. So when you're doing your laboratories, when you're comparing your length of your pendulums, and you're calculating the acceleration due to gravity, you can do that by looking at your simple pendulum and bringing that back into the simple harmonic motion.